Use the known amorphous ices has led scientists to suggest water in fact exists as two liquids at very cold temperatures, and that theoretically, at a certain temperature, both of these liquids could coexist, with one type floating above the other, as when mixing oil and water. This hypothesis has been demonstrated in a computer simulation, but not confirmed by experiment. The researchers say that their new study may raise questions about the validity of this idea. Professor Salzman said, existing models of water should be retested. They need to be able to explain the existence of medium-density amorphous ice. This could be the starting point for finally explaining liquid water. The researchers proposed that the newly discovered ice may be the true glassy state of liquid water, that is, a precise replica of liquid water in solid form, in the same way that glass in windows is the solid form of liquid silicon dioxide. However, another scenario is that MDA is not glassy at all, but is in a heavily sheared crystalline state. Co-author Professor Andrea Sella, UCL Chemistry, said, "We have shown it is possible to create what looks like a stop-motion kind of water. This is an unexpected and quite amazing finding." Lead author Dr. Alexander Rosufinson, who carried out the experimental work while at UCL Chemistry, said, "We shook the ice like crazy for a long time and destroyed the crystal structure. Rather than ending up with smaller pieces of ice, we realized that we had come up with an entirely new kind of thing, with some remarkable properties." By mimicking the ball milling procedure via repeated random shearing of crystalline ice, the team also created a computational model of MDA. Dr. Michael Davies, who carried out the computational modeling whilst a PhD student in the ICE, Interfaces, Catalytic and Environmental, lab at UCL and the University of Cambridge, said, "Our discovery of MDA raises many questions on the nature of liquid water, and so understanding MDA's precise atomic structure is very important. New form of ice is like a snapshot of liquid water. A new form of ice very similar in molecular structure to liquid water, left, compared to ordinary crystalline ice, right. Credit, University of Cambridge. Water has many anomalies that have long baffled scientists. For instance, water is at its most dense at 4 degrees centigrade and becomes less dense as it freezes, hence why ice floats. Also, the more you squeeze liquid water, the easier it gets to compress, deviating from principles true for most other substances. Amorphous ice was first discovered in its low-density form in the 1930s when scientists condensed water vapor on a metal surface cooled to -110 degrees centigrade. Its high-density state was discovered in the 1980s when ordinary ice was compressed at nearly -200 degrees centigrade. While common in space, on Earth, amorphous ice is thought only to occur in the cold upper reaches of the atmosphere. Medium-density amorphous ice. Screenshot from video, below, showing the jar with medium-density amorphous ice inside, with steel balls and liquid nitrogen. Credit, Michael Davies. Ball milling is a technique used in several industries to grind or blend materials, but had not before been applied to ice. In the study, liquid nitrogen was used to cool a grinding jar to -200 degrees centigrade, and the density of the ball-milled ice was determined from its buoyancy in liquid nitrogen. The researchers used a number of other techniques to analyze the structure and properties of MDA, including X-ray diffraction, looking at the pattern of X-rays reflected off the ice, and Raman spectroscopy, looking at how the ice scatters light, at UCL Chemistry, as well as small-angle diffraction at the UCL Center for Nature-Inspired Engineering to explore its long-range structure. How to make medium-density amorphous ice, MDA. By repeatedly shearing hexagonal ice, we can create MDA. Furthermore, they used calorimetry to investigate the heat released when the medium-density ice recrystallized at warmer temperatures. They found that, if they compressed the MDA and then warmed it up, it released a surprisingly large amount of energy as it recrystallized, showing that H2O can be a high-energy geophysical material that may drive tectonic motions in the ice moons of the solar system.